Okay, welcome everybody to the next lecture on algorithmic meta theorems. Today we're going to actually talk about the part that I like the most, bounded expansion and avoidance graph classes. So a quick recap. So in the last lecture, we learned about Geifmann's locality theorem and locally bounded tree-width graph classes, and showed that you can do using Geifmann first-order model checking on locally bounded tree width in FPT time. So locally bounded tree width were those where you take balls of radius r, and the tree width of these balls needs to be bounded by a function of r. And this captures, for example, of course, normal bounded tree width, and also planar graphs and bounded degree graphs. For example, in bounded degree graphs, every ball of radius r has only constant size, and therefore only constant tree width. And this would show that they have locally bounded tree width. However, locally bounded tree width is not very robust. So if you add an apex vertex, for example, to a grid, then it no longer has locally bounded tree width. And the meta theorem doesn't give us any algorithmic application anymore. However, we know that if you have a graph and you can do model checking on it, then you can still do model checking after adding an apex vertex to the graph. So by this, we know that locally bounded tree width is not yet the final answer to our question for the exact characterization of sparse graphs which admit FPT model checking. So this is our quest. Like, we're looking for the right notion of sparsity, such that we can say a graph is sparse if and only if it has a structural characterization, if and only if you can do FPT first order model checking on these kind of graphs. And for the next lectures, we're going to talk about this topic and resolve it. But I would also like to make some advertisement. So there's a very nice lecture that is available on YouTube, and the lecture notes are also available on the internet. And they go into great depth about sparsity and lower denseness and bounded expansion and all these related topics. So I can highly recommend this if you're not yet fully satisfied after this lecture and want more information on this topic. Okay. So we will have to make some design decisions when we talk about what a sparse graph is. And the first thing is you could kind of cheat by subdividing every edge. And this way you can say, okay, well, now the average degree is bounded. For every two edges, you have at least one vertex. So the average degree is at most 2. And you can say, okay, now the graph is sparse. And we have to decide whether we accept this now or if we would reject this and say, well, basically it's the same graph, just subdivided, so we shouldn't call it sparse. And if we consider such a subdivision of an arbitrary graph sparse, then we end up with what we call degeneracy, and otherwise we end up with bounded expansion and lower dense graph classes. So at first, I would assume that we consider such a graph sparse and see what kind of world we end up in, and then maybe backtrack and see that we did the wrong decision, and then say, okay, this graph, we shouldn't consider it sparse. But for now, let's say a subdivision of arbitrary graphs are considered sparse. Then the next question we would have to ask ourselves, what about adding extra vertices? Just putting a bunch of extra vertices at the side, like n squared many. Now the average degree would also be bounded, and we would wonder, is such a graph sparse? But I feel like this is too much cheating. So we should forbid making a graph sparse by just adding a bunch of isolated vertices on the side. So this is something we want to forbid. And what does it mean formally? We want to say that we want to find a Witch measure which is closed under taking subgraphs. So adding more vertices should never make a graph more sparse, or phrased other way around, removing vertices should never make a graph less sparse. So the width measures that we want to define, they shouldn't increase if you remove vertices, or if you talk about graph classes, if you are in a graph class and remove a vertex, you should stay within this graph class. So this is a sensible choice for sparse graphs, or in general. And a graph class which is closed under taking subgraphs is something that we also call hereditary graph classes. And we from now on look for an hereditary width measure that captures our sparse graphs. And here there is basically only one option that we can go with, and the right notion here is degeneracy. Some of you may have heard of it already, and we say that the degeneracy of the graph is the minimum number k, such that there is an ordering of the vertices where no vertex has more than k neighbors on the left. And if we have a degeneracy ordering, we usually draw it like this on the line, and here this is the rightmost vertex, and it should have only k neighbors on the left. So here it has only 2 neighbors on the left, and every vertex here basically has only 2 neighbors on the left. And this is why we say this graph has degeneracy at most 2. So, and the degeneracy, or like the degeneracy, is the minimum number of left neighbors in an optimal ordering of the vertices of the graph. And if you want to construct such a degeneracy ordering, usually you want to place the vertices with a very low degree. You want to place them on the very right. But a vertex on the very left, this one, for example, it can have a very high degree. For example, it can have a lot of neighbors, but if all the neighbors go to the right, then they don't count into the degeneracy ordering. So the vertex with a very high degree, as long as it is all the neighbors go to the right, the graph can still have bounded degeneracy. And here's some example graphs. So let's start with a single star. Can anybody see the degeneracy of a star? What would that be? What would a good ordering be? So we can order the vertices like this. We put all the degree 1 vertices on the right, and the center vertex will be the leftmost vertex. And now every vertex has at most 1 neighbor on the left, which means the degeneracy of the star is at most 1. So this would be a very good ordering for the degeneracy. This would obviously be a very bad ordering of the degeneracy, because now this vertex here has a lot of neighbors on the left. So this ordering would be high degeneracy ordering. So it would be better to go with this one. And we said that we wanted a width method that is closed under taking subgraphs. So removing vertices should never increase the degeneracy. And this is the case here, obviously, because let's take the graph here at the top, and we have a degeneracy ordering at the bottom. And if you remove this degeneracy ordering I think the graph is now degeneracy at most 4. And if you remove a vertex, you can just remove it from the degeneracy ordering, so on and so on. And you see that the graph still has degeneracy at most 4 after removing some vertices. Yep, a question?
Is it trivial or straightforward to see how such an ordering can be obtained?
Yeah, that's the next slide. First, one more remark. So the degeneracy kind of generalizes the average degree to subgraph closure, because you can show that if the degeneracy is most k, then all subgraphs have average degree at most 2k. So this not only bounds average degree of the whole graph, but also the average degree of every subgraph, which is something that we would need for subgraph closed width measures. And now we can talk about computing such a degeneracy ordering, and it is actually quite straightforward. If the degeneracy is at most k, then there is always a vertex which has at most k neighbors in total. So this would be the vertex that will be placed to the very right of the ordering. So you can construct this ordering by just taking the vertex with the minimal degree and place it to the very right of the ordering. And now the graph is updated. This vertex here is removed, the one we've extracted already, and we repeat it. We again take out a vertex with minimal degree, again and again and again. And in the end, this is always an optimal degeneracy ordering obtained this way. So that's very nice about degeneracy. It's easy to compute, and it's not so difficult to understand. So can anybody say something about the degeneracy of planar graphs?
It's at most 6, because in a planar graph there's always a vertex with degree at most 6. And then when we remove this vertex, then we still have a planar graph and can continue with this argument.
Exactly. So we can even do it with degree at most 5. So every planar graph has a vertex of degree at most 5. And we can always extract that and put that to the very right of our degeneracy ordering. So planar graphs have bounded degeneracy, exactly. But now we come to the bad news. So unfortunately, model checking is hard on graphs of bounded degeneracy. So degeneracy is too general to describe the tractable graph classes. Already on graph with degeneracy at most 2, first order model checking cannot be done in FPT time. And how would we prove that? Let's reduce from parameterized clique problem. So the k-clique problem is where we have a graph and we want to decide if there are a clique of size k, and k-clique cannot be solved in time f of k times into the c under standard complexity theoretic assumptions. And now we want to assume that we can do first order model checking at FPT time and conclude that we then could also solve cliques or solve the FPT clique problem on arbitrary graphs. So we want to use and we want to assume we have a model checking algorithm for degeneracy 2 graphs and now solve the clique problem with it. How would we do this? So what we can do is we subdivide every edge of our graph in which we want to find a clique. And so we see we add here some purple vertices. And now the graph has bounded degeneracy, because you can always order the vertices of the clique like it is drawn here in the bottom. So on the very right, you place the purple subdivision vertices. All the purple vertices have degree at most 2, so they have at most 2 neighbors to the left. On the other hand, all the black original vertices, they get placed to the very left. And since the black vertices are only adjacent to purple vertices, they have no left neighbors. All the neighbors go to the right. So even though the black vertices can have a lot of neighbors, these neighbors do not increase the degeneracy because they go towards the purple vertices on the right. So we see now the graph has degeneracy at most 2, but it's just a subdivision of the original graph. And so instead of looking for a clique, we can now look for k black vertices that have distance at most 2. And this is something that is expressible in first order logic. You say there is x1 to xk, and I call it black. And for every pair of them, there exists a purple vertex that is adjacent to both of them. And now if you could evaluate such a formula in this running time, f of phi times n to the c, then you could also solve k-clique on arbitrary graphs in FPT time, and this is a contradiction. So model checking is hard on graphs with bounded degeneracy. That's the takeaway here. So we have to reconsider our decisions in the very beginning. In the beginning, we said, okay, let's assume subdivisions are sparse, but now we have to say no subdivisions. We have to say they're not sparse because otherwise degeneracy is where we would end up with, and their model checking is hard. So the real problem here, why we cannot allow subdivisions to be sparse, is because first order logic can recover the hidden graph. So you take a graph and you kind of hide it by subdividing the edges, but first order logic can undo this subdivision by just asking whether 2 vertices have distance 2 instead of asking whether they're adjacent. And this not only works for subdividing an edge once, it also works if you subdivide an edge 3 times or k times or any constant number of times. First order logic can always undo this by asking whether two vertices have a short path that connects them. So it can recover the graphs that hide at a certain depth. So that's why we have to enforce that the subgraphs that hide at a certain depth need to be sparse as well. And soon we will notice that the right notion to characterize these subgraphs that hide at a certain depth will be called shallow minors. But before we can introduce shallow minors, we first have to talk about normal minors, which are a little bit less complicated. So let's talk about minors. So we say a graph H is a minor of a graph G, also written like this, H smaller than G, if you can obtain H from G by a sequence of relatively simple operations. So one thing you can do is you can merge two edges. You can merge an edge. So here you have an edge between red and what's green is the other color. And merging the edges means you turn this into a single vertex whose neighborhood is the union of the neighborhoods of the two endpoints. So it's the intuitive merging operation that you would think of. And the other two operations are even simpler. You are also allowed to remove edges or to remove vertices. And if you can obtain H by a sequence of such operations, then we call H a minor of G. And here's an example. This square is a minor of the graph on the right. And how can we obtain the square via these operations? First, we could remove this pendant vertex. And next, we could merge this edge, merge this edge, merge this edge, and merge this edge. And what we would end up with is the triangle. But there's a different way to visualize these minors, and this will be a bit more useful in the future. And so we can also say that a graph is a minor if it can be built from a certain host graph using the following operations. At first, you can pick some connected subgraphs. So here, every gray area is a connected subgraph that I've picked. Second operation is you can remove all vertices that lie outside these subgraphs. So here, for example, this vertex is removed. Second thing is now, or the third thing is that you contract these subgraphs into single vertices. So you contract them by moving them slowly closer together, and in the end, they merge into a single vertex, and this is going to be the minor. Additionally, you're also allowed to remove some other edges afterwards, and that's why we see now that this house graph is a minor of this original graph. And this is equivalent to the characterization or definition of minors that I gave you beforehand, but maybe a bit easier to reason about. And are there any questions so far? If not, then we can use minors to characterize graph classes as well. So maybe the most famous result would be Kuratowski's theorem, which states that a graph is planar if and only if it does not have a K33 or a K5 as a minor. So K33, complete bipartite graph with halves of 3 vertices each, or a clique of size 5. So instead of saying graph is planar, we can instead say this minor or that minor should not occur in a graph. So we can characterize it by forbidding a set of minors to occur. And you can go on. For example, graph is forest if it does not contain a K3 as a minor, because you can always contract a circle into K3. So K3's minors are equivalent to circles in a sense. So this way you can characterize forests. Tree width 2 would be characterized by excluding K4 as a minor. And if you want to go further, tree width 3 can be characterized by saying that none of these, or that a graph has tree width at most 3 if it does not have any of these graphs as a minor. So all of these need to be forbidden. And you can push it even further, you can say for every k, there exists a family of minors fk, such that the graph has true width k if and only if it does not have any graph from fk as a minor. So you can build such characterizing minor families for graphs with bounded tree width. So we could use this now to define graph class. For example, now we can say graph class C is minor free if there exists a constant t such that every graph in C excludes the clique on t vertices. So we want to exclude a fixed clique. And this concept characterizes or generalizes something, the stuff that we discussed already. So every planar graph or every graph with bounded tree width is minor free. And this is easily seen for planar graphs. So if a graph is planar, then it does not have the k33 or it doesn't have the k5. And this means in particular that it also doesn't have the k6 as a subgraph. So the k33 and the k5, they both have 6 vertices at least. So assuming that you had the k6 as a minor, then you would also end up with this or with this as a minor. So minor, by excluding a fixed clique, you can characterize quite general classes of graphs. And now this sounds like an idea to our original problem. So we had the problem that first order logic can recover the graphs that hide at a certain depth. And with minors, we can forbid graphs occurring at deeper depth. And so can we now say that sparse graphs are exactly those which are minor free, which exclude some kt, some clique of size t as a minor? Unfortunately, this is not yet the whole answer, because this way we could not capture locally bounded tree width this way. So last lecture, we introduced locally bounded tree width, and we also introduced this class of graphs, which we proved to have locally bounded tree width. So we said the class of all cliques, of all log n subdivisions of cliques of size n, they had locally bounded tree width. But you can show that these graphs are not minor free. So here, every edge is subdivided log n times, and you take these log n subdivisions of cliques of size n for all n. This is a class with locally bounded tree width, but it is not minor closed. So how can we see that it contains arbitrarily large cliques as a minor? So what you can do is you can take these high degree vertices and then draw these minor regions by taking not only the high degree vertex, but also taking half of the subdivision vertices that are adjacent to it. So this way, for every high degree vertex, you can create such a gray area. And on a clique of size n, you would have these n neighborhoods or n gray balls. And if you would contract them, the result would be a clique of size n. So such a graph has now a clique of size n as minor. So this class is locally bounded tree width. It contains arbitrarily large cliques as a minor. So we cannot just forbidding a certain minor is not enough to capture all classes that are tractable, have tractable first order model checking, because this class here is not minor free, but on it you can do first order model checking in FPT time. So let's track back what our original graph goal was. So we want to characterize exactly those graphs for which you can do first order model checking.
Sorry.
Yeah. Question?
Can I ask a question? So that means that minor free just means that I can find for a fixed constant clique of that size that's definitely not in any graph of the class. It doesn't mean that the class needs to be characterized by exclusion of that particular clique.
Yeah, it's not an exact characterization.
Okay.
So yeah, we say a class is minor free if every graph in the class excludes, or if there exists a constant t, such that every graph in the class does not have kt as a minor. Yeah, that's it. And what we wanted is we wanted to exactly characterize those sparse graph classes for which you can do first order model checking. And we're considering those graph classes that are closed undertaking subgraphs. And now we have two examples which we need to be very careful about. So we know that if you subdivide a clique log n times, then this class has locally bounded tree width, and you can do first order model checking on it. On the other hand, if you take a clique of size n, or take the class that contains all k subdivisions of cliques of size n, where k is a fixed constant, this class here, then on this class, first order model checking is hard. Because we assume that it is closed undertaking subgraphs, so you could remove some of these subdivision vertices. This way, the graph not only contains the k subdivisions of all cliques, but it also contains the k subdivisions of all graphs. This is now because we assumed closure under subgraphs. So the class would contain the k subdivisions of all graphs. And before, we talked about how first order logic can undo these or can skip over this path of length k. So instead of asking whether two vertices are adjacent, you can ask whether there exists a path of length k that connects these vertices. So if you could solve the model checking problem on these k subdivisions, then you could also solve, for example, clique on all graphs. So this is now quite a rigid limitation that we have. We have to forbid k subdivisions, but we can allow, or we have to allow, log n subdivisions if we want to exactly characterize classes for which you can do FPT model checking. So, yeah.
So just a small question or clarification. So we want to permit larger subdivisions because then it becomes harder or impossible for the first order model checking to undo the subdivisions. Is that right?
Exactly. Yeah.
Okay. Thank you.
So if you wanted to undo a subdivision of length log n, then you would need a formula which has also length log n kind of to undo the subdivision. And now you have a formula that grows with n, and this is something that we don't have to consider in our framework. We only consider formulas of constant length. So now we have to formalize minors that hide only at a certain depth, a low depth. This is something that we call shallow minors. So we say H is a depth R minor of G, also written H depth R minor of G like this, if H can be built from G by now a different set of operations. The key difference is now that we can, instead of picking arbitrary connected subgraphs, now we're only allowed to pick connected subgraphs with radius at most R. So in this example, we want to build a depth 2 minor of G. This is why we pick these gray areas with radius at most 2. So this is the first operation we can do. Pick connect subgraphs with radius at most R. Next, we remove all vertices that lie outside these subgraphs. And again, we are allowed to contract each subgraph into a single vertex, and optionally also remove some edges afterwards. And the result, if each subgraph had radius at most r, is what we call a depth r minor. And with this, we have now all the ingredients to define our sparse graph classes. So we will want to bound the sparsity of depth r minors as a function of r. And this goes back to Neschetri and Osama de Mendes, who pioneered these new concepts and who were the first to consider using these depth r minors to characterize sparse graph classes. And the way we can use them is twofold. For example, one way would be to consider the average degree of depth r minors. And this is something that we denote by nabla r of graph G. So nabla r, or the average degree at depth r of a graph, will be the maximum over all average degrees of depth r minus in G. So you consider all depth r minus of G, so all the minus that you can build using this radius r ball construction we considered on the last slide, and then you compute the average density of these vertices. So it's not quite average degree, but the density. So the number of edges divided by the number of vertices. And this is the width measure that we call nabla r of G. So this, in a sense, bounds the sparsity of the minus of depth r in a graph. This is one way to do it, by requiring that the minors have bounded average degree. And the second way of doing it would be to consider the clique size of minors. So by omega r of G, we denote the size of the maximal clique that occurs as a depth r minor in the graph. So these two definitions on the first glance, they look a bit confusing, but they will turn out to be just the right tool to characterize sparse graphs. So for every r, we can now define the depth r average degree and the depth r clique size. And for the case where r is 1, then it is simply the largest one shallow minor of G would be G itself. So if r is 1, this would simply be the average degree and the maximum clique in the graph. But at larger depth, we consider deeper and deeper minors, and the notion gets a different meaning. And if we define these two concepts, we can now use it to define bounded expansion in lower dense graph classes. So the definitions are quite similar. We start with bounded expansion. We say that a graph class C has bounded expansion if there exists some function f of r such that the average degree at depth r is bounded as a function of r. So similarly to bounding the clique, the tree width of the R neighborhoods for locally bounded tree width, we now bound the average degree for a certain R. So as R gets larger and larger, the average degree may also get larger and larger, but it needs to be bounded by some function of R. It cannot grow with n, with the size of the graph. It can only grow with R. So by bounding the average degree of a graph class for every R, we end up with bounded expansion. And similarly, if we bound the clique size of R, depth R minus we end up with nowhere dense graph classes. So the definition is almost the same, except now that we require that for all R, the clique sizes of R shallow minus needs to be bounded by a function of R. So for bounded expansion, we bound the average degree. For nowhere dense, we bound the clique size of R shallow minus. So let's take a look at an example here. So here we again have these two graphs and two graph classes, and let's consider the R shallow minors of these graphs. So for the graph here on the right, we showed that K is K minor of this. So if you're looking at minors of depth K, that, or sorry, if you're looking at minors of depth K, then this graph on the right contains the clique on n vertices as a minor. So if you look at the K minors of these graphs, it contains all graphs. All graphs occur as K minors. So in particular, the K minors have unbounded average degree and unbounded clique size. So such a graph class would not be considered to have bounded expansion or nowhere dense. Bounded expansion, nowhere dense, we require for every R, the minors to be simple. But now here we have a counterexample. If we set R to K, then the minors grow arbitrarily large and arbitrarily dense and contain arbitrarily large cliques. So this graph on the right would not have bounded expansion and nowhere dense. However, if we look at the graph on the left, this will fit our notion of sparsity. So if we now look, assume for example that R is at most log n divided by, I don't know, 100. Then the R shallow minors, they cannot contain these very large parts. So the R shallow minors, they can only contain some small bits of these subdivisions. So maybe they look like this. These regions can be contracted, perhaps. So this means if you take R shallow minors of this graph, assuming that R is bounded by at most log n divided by 100, then the R shallow minors are again subdivided cliques. So they're no longer log n subdivided cliques, but maybe subdivisions by some other length, but still they're subdivided cliques, and subdivided cliques contain no large cliques and have a low average degree. Yeah, question?
So what were the rules again for taking these R shallow minors? Because it's apparently not repeated application of the same thing, because otherwise I could contract all of these and then again take a subgraph, contract and repeat. This is obviously not intended.
So you can only do this contraction once in parallel for all the gray regions that you picked.
Okay.
So now you can pick here these regions with radius at most R that I've circled around. And then a single time, all of them together, you contract each region to a single vertex. And the result would still be a subdivision of a clique. And you cannot do it multiple times. At least not if you're looking for R shallow minors. So if you take an R shallow minor of an R shallow minor, you would probably get like a 2 R shallow minors. So if the radius is bounded by log n divided by 100, then all R shallow minors are sparse. On the other hand, if say the radius is larger than log n divided by 100, then you can bound the number of vertices as a function of r. So then n is smaller than, what is it, 2 to the 100r. So now we have bounded the number of vertices as a function of r. And if the number of vertices is bounded by a function of r, then also the clique size and the average degree, everything is bounded as a function of r. So if r is relatively large, then we also have bounded clique sizes and average degree of the r shallow minors. So this is again this strange trick of making the case distinction on r, but it works in our favor here. So any questions about this so far? If not, then we can now finally see that we have reached our limit in our quest of looking for an exact characterization of graph classes that admit FPT model checking. And there is this very beautiful result by Kohlkreutzer and Sieberts, which basically says nowhere dense graph classes are exactly those subgraph closed graph classes for which you can do model checking. So let's dissect this statement slowly. So here we say for every graph class C that is closed under subgraphs. So we only consider those graph classes which are closed under subgraphs, meaning if you take a graph from the class, you remove an edge or a vertex, and then you stay within the graph class. So for those graph classes that are closed under subgraphs, the following holds. C, the class, is nowhere dense if and only if the first order model checking problem on C is FPT. So we have an exact characterization of those graph classes where you can do FPT model checking. FPT means again f of phi times n to the c. And you can do this if and only if the class is nowhere dense. So nowhere dense is the last answer you can find if you're looking for graph classes that are closed under subgraphs, which is something that makes sense for sparse graphs. This is, of course, a relative statement, so you assume some complexity, theoretic standard assumptions, like FPT is not equal to W1. So if you assume that, then the statement is true. So this is why the result is so nice. We have finally found the answer of what you can do on sparse graph classes in terms of model checking, and the answer is nowhere dense is the limit. And in the next lectures, we will try to prove some of these results. So for nowhere dense, we will not be able to prove this result, but at least for graph classes with bounded expansion, we will go through the proof of model checking. But first, maybe we should talk a little bit more about some structural aspects, talk about how general these classes are and how they relate to other classes that we talked about already, like bounded degree, planar graphs, and all these. They will all have bounded expansion and nowhere dense. And for the rest of the lecture, I would like to prove this. And the picture that we will see is this nice picture by Felix. And so nowhere dense graph classes will be at the very top of the hierarchy. And below, you have bounded expansion here. Bounded expansion will, for example, be not comparable to a locally bounded tree width. So there exists graphs which have locally bounded tree width, but not bounded expansion, or graph classes which have locally bounded tree width, but not bounded expansion, and the other way around. But still, bounded expansion generalizes, for example, bounded tree width, planarity, and bounded degree. So the first thing that I wanted to talk about is this relationship. So every class that is bounded expansion is also nowhere dense, but on the other hand, there exist nowhere dense classes that do not have bounded expansion. So let's maybe try to prove this. Or other questions about this relationship so far? So
in this picture, it
Yeah.
looks like bounded tree width is not contained in locally bounded tree width, but that's not right.
that is not right. Yeah. Never checked each and every connection in this picture, but yeah, there should be a connection like this. Bounded tree width is contained in locally bounded tree width. Good point.
So that's funny. I've seen this picture a lot of times and I only noticed this now.
Maybe we should issue a pull request for this picture. So first, let's prove that every class with bounded expansion is also nowhere dense. So how do we prove this? We assume that class C has bounded expansion, and let's say f of r is the function that bounds the average degree of minus at depth r. So here, nabla r is bounded by f of r for every r. Then now we want to show the following, that the clique size at depth r is also bounded by twice the average degree plus 1. So if we also find a bound on the clique size of depth r minus, then in particular the class would also be nowhere dense. So how do we prove this? We want to show that if the clique size is large, then also the average degree is large. This then implies a statement. So let's assume that the clique size at depth r of a graph G is exactly t. Then this means kt is depth r minor of G. So this depth r minor, this means that the average degree at depth r is at least the number of edges in the kt divided by the number of vertices in the kt. So since the kt is a minor, this one is a lower bound for the largest average degree. And now we can plug in the numbers. The kt has t vertices and every edge is present, so the number of edges is t divided by t minus 1/2. Or in other words, if we cancel out the t, the average degree of depth r minus, it's at least t minus 1 times 2. And if we now multiply by 2 and add 1, we see that the clique size is at most twice the average degree plus 1. So just simple arithmetics basically so far. And from this on, the rest of the statement follows exactly, easily. So the size of r shallow cliques is at most 2 times f of r plus 1, because f of r is a bound on nabla r. So now we've bounded the size of r shallow cliques as a function of r only, which means that the class C is also nowhere dense. So now we see every class with bounded expansion is also nowhere dense, but the converse of the statement does not hold. So there exist graph classes which are nowhere dense, but do not have bounded expansion. These graph classes are sometimes not so easy to see because they all follow a common theme. And basically these classes, they have a high average degree, but they also have high girth. So high average degree is clear what it means. Every vertex has like degree, for example, log n, and the average degree is log n, but the girth is the length of a shortest cycle. So if the shortest cycle has length at least log n, this means if you take a vertex and the neighborhood around this vertex with radius, let's say log n third, then such a neighborhood needs to be a tree. So if the largest, if the shortest cycle has length larger than log n, then the neighborhoods of radius log n third are trees. That's basically what this says. So this is something that we will exploit soon. But we will make a probabilistic argument. We will construct this graph class that is nowhere dense but does not have bounded expansion using probability. And it will basically be a random graph where each edge is present with a probability of log n divided by n. So looks quite similar to what we did in the exercise. If every edge is present with the probability of log n divided by n, then the expected degree of a vertex is 2 times log n. Because there's n possible edges and each has a probability of log n divided by n, then the expected degree is 2 times log n, or is it just log n actually? Anyways, so with high probability, the average degree is unbounded of the graph. And this means already for r equal to, what is it, 1 or 0, the minors have unbounded average degree, and therefore the class does not have bounded expansion. So if a class has unbounded average degree, then it can never have bounded expansion. So first property of not having bounded expansion is satisfied by our random graph, but next we want to show that it is nowhere dense. I'm a little bit fuzzy here, I know that. So with these probabilistic arguments, you usually have to be very careful, but I just want to get the general picture across. That's why I will be not very precise with these probabilistic arguments, and I will swallow a lot of constants within what I'm talking about next. So let's next consider the probability that k vertices form a cycle. So the probability of each individual edge is log n divided by n, and the cycle contains k vertices, so k edges. So the probability of the cycle is log n divided by n raised by k. So we can use this to bound the expected number of k cycles. So there's 2 to the k possible cycles, and each has a probability of log n divided by n to the k. So n to the k and this n to the k, they cancel each other out. So the expected number of k cycles is roughly log n to the k. And what we can do next, we remove all cycles whose length is at most, let's say, log n. So we know that the expected number of these cycles of length log n is bounded by log n to the log n. So there's not so many cycles of this length. So we can just remove all of them, and the graph did not change too much. So in particular, by removing these cycles, we've only removed some vanishing fraction of the vertices. So the expected degree is still rather high. So with high probability, we're still within a class which does not have bounded expansion. But we will see that our class will be nowhere dense now. So every log n neighborhood in the graph will look like a tree. So this means that every log n divided by 6 shallow minor is triangle free. So if you have such a minor of log n divided by 6, then you take a vertex here and you take some blob, and this blob has length as radius at most log n divided by 6. And then assuming there would be a triangle, then 3 of those blobs at least would need to touch together, and there's 6 such paths of length at most log n divided by 6. So in total, you would have a cycle of length log n. But we assumed that we removed all those cycles, so we have a contradiction. So the log n divided by 6 minors, they cannot contain triangles, so they're triangle free, which means that the largest clique size in R shallow minors is at most 2, if we assume that the radius is small. So if our radius is bounded by log n divided by 6, then all R shallow minors are triangle free, and this bounds omega r by at most 2. This was the first half of the case distinction. Second half of the case distinction is the other way around, where we assume that R is larger than log n divided by 6, but this means that the size of the largest R subdivided clique is at most n, is at most 2 to the 2 to the 6r. So this is, in this case, we're also bounded by a function of r. And this completes a very rough description of the proof. So the graph class is with high probability nowhere dense. So if you want to make this formal, it will be a bit more messy, but this is the general picture. You remove all the short cycles, and with high probability, you still have average degree. So now we've proven this part of the picture. We've separated nowhere dense from bounded expansion graph classes. Next, I would like to show graph classes with bounded degree also have bounded expansion. So here we have this line up here. And how do we prove the bounded degree graph classes have bounded expansion? We show that the average degree of R, so we assume that we have a graph G of degree at most D, and we show that the average degree of R shallow minors is bounded by at most D to the R plus 2. If this is the case, then the average degree of depth R is bounded by a function of R, and we have a bounded expansion graph class. So how do these depth R minus look like? We had these subgraphs of radius R, and we contracted each of them into a single vertex, and this yields the structure of our minor. So let's take a look at one of these subgraphs of radius R that we contract while building our minors. So one of these subgraphs may look like this. It has radius at most R, but this also means that because the radius is bounded and the graph has degree at most D, the subgraph has size at most D to the R plus 1. So each of these subgraphs with small radius has small size. And additionally, therefore, each of those subgraphs can only have a small number of neighbors. So there's only D to the R plus 1 vertices inside there, and each of them can only have D outgoing edges. So in our minor model, we will have each subgraph that has been contracted will only have at most D to the R plus 2 neighbors. And if you bound the average degree of an R shallow minor like this, then the proof is complete. Or we bounded actually the maximal degree, but this also bounds the average degree. Okay, so we ticked off bounded degree. The other two natural things that we considered so far were planar graphs and bounded tree width graphs. We want to show that they also have bounded expansion. And we can go the route via H minor free graphs. Earlier, we mentioned that graph classes that have bounded tree width are minor free, so they exclude some fixed clique, and planar graphs are also minor free. So if we show that minor free classes have bounded expansion, then in particular classes with bounded tree width and planar graphs have bounded expansion. So we want to show the following statement, that pick a graph.
I would have a quick question. Shouldn't it be exclude some minors and not a single one? Or is there no difference?
There is no difference. So if you exclude some minor, so if you have a family of forbidden minors, let's say A with 10 vertices, B with 15 vertices, then you can take clique on 15 vertices, and by excluding this clique, I think you exclude both A and B. Does it make sense?
Yeah, but then my graph class would also be smaller, because in my, well, am I wrong that I would exclude some additional cases? So I would make my graph class smaller by excluding a bigger one.
I see. Yes, I'm a little bit confused by this right now. I think we will have to come back to this at the next lecture. Yeah, I thought I could maybe simplify the proof by assuming that only a single minor is excluded, but right now I don't see the argument anymore why that works. Yes, I will have to come back to that afterwards. But for now, I think we have to assume that C is a class that excludes some fixed minor.
Okay. Thanks.
Yeah, good to be attentive there. So I will have to read up on this and come back to it. So, okay, now we assume that C is minor free, meaning that some fixed KT is excluded in all graphs of C. So then we can pick some arbitrary graph from the graph class, and we know that it doesn't have KT as a minor. And not only does G not have KT as a minor, but every R shallow minor of G does not have KT as a minor. So let me see if I can draw a picture of this. So if we take an R shallow minor G prime of G, and if we assume for contradiction, if this minor of G contained KT as a minor, then the minor relation is transitive. Not only G prime would contain T as a minor, but also G itself would contain KT as a minor. Because if something is a minor of a minor, then it is also a minor of the original graph, because it can compose these contraction operations. So this way we can conclude that also the R shallow minors of G exclude KT. And on the next slide, I will introduce some extra lemma, which basically says that every graph that does not contain KT as a minor has bounded average degree. It will have at most 2 to the T edges per vertex. And if we assume for now that this was true, then every R shallow minor of G excludes KT as a minor, and therefore has at most 2 to the T edges per vertex. And in other words, this bounds nabla R of G by at most 2 to the T. So this is a very strong bound on nabla R because it is independent of the radius. So usually you would bound it by f of R, but now f of R is a constant. F of R will be 2 to the T. So to complete the proof that minor free classes have bounded expansion, we will have to prove this step here. And statement.
This is on average, right? Not for an individual vertex.
Yes, it has at most so and so many edges per vertex. So the number of edges divided by the number of vertices will be at most 2 to the t.
Okay.
Thanks. So the last missing part is to prove that for every t, if a graph does not contain kt as a minor, then it has at most 2 to the t edges per vertex, which means the edges of G divided by the vertices of G is at most 2 to the t. This is something we have to prove. And we want to prove it by induction. So it will be induction not only on the number of vertices, but also on the number t. And we proceed as follows. Since I take a G which excludes some kt, and we pick some vertex v of the graph. And next, we take a look at the neighborhood of this vertex v. So we take all the vertices that are adjacent to v, but not v itself. So this will be this darker gray area here. And now this graph excludes not only a kt, but it also excludes a kt minus 1. Because assuming you had a kt minus 1 here, then by adding the vertex v, you could turn it into a kt in the whole graph, but we assume that there is no kt, so this is a contradiction. So by adding the vertex v, we can always increase the clique size of a minor inside the darker gray area. So now in this neighborhood of v, we exclude the kt minus 1. And now we can use the induction hypothesis. Because t is 1 smaller, we can conclude that this area here has at most 2 to the t minus 1 edges per vertex. This is just applying the induction hypothesis. So it has bounded average degree. And what we can do now is we pick a second vertex inside this area. And this one will be the vertex with the lowest degree. And there will always be a vertex whose degree is at most twice the average degree. And this will be our vertex u. So this vertex has degree at most 2 to the t, at least within this neighborhood of v. So here, this area will be the neighborhood of u within the neighborhood of v. So it will be all the vertices that are both adjacent to u and adjacent to v, and there is at most 2 to the t of them. So we can simplify the picture like this. So far, we have shown that there's a vertex u, vertex v, and the neighborhood between those two vertices is rather small. There's at most 2 to the t vertices that are adjacent to both of them. And what we can do now is we contract u and v together. So move them together like this until it looks like this. And now this is a graph that contains one vertex less. We have contracted 2 vertices into 1 vertex. So this graph contains 1 vertex less, and we can again apply the induction hypothesis. So this graph also has at most 2 to the t edges per vertex. But we are not interested in this graph. We want to show that this graph has 2 to the t edges per vertex. So what we do now is we undo the contraction. We pull the 2 vertices apart again. So now we have 2 vertices v and u. We split them apart again. And this introduces 1 extra vertex. So starting from this graph, by pulling them apart, we add 1 extra vertex. And we also add a bunch of extra edges. So in particular, these vertices here in the gray area, before they had only one edge to the merged vertex, but now they have two edges, one to U and one to V. So for every vertex in the intersection of the neighborhood, or for every vertex that is adjacent to both U and V, we add one extra edge by pulling U and V apart. But there's only at most 2 to the T many vertices that are adjacent to both. So we add at most 2 to the T edges. So we add one vertex and at most 2 to the T edges. So in total, we still have the property that there's at most 2 to the T edges per vertex. So this then completes the statement. This statement was the last building block in our proof. And this way we have shown that every graph class that excludes one fixed clique as a minor has bounded expansion. This way, classes with bounded read width, planar graphs, bounded degree graphs, they all have bounded expansion and are all nowhere dense. So basically, nowhere dense graph classes generalize everything we've talked so far. Bounded expansion graph classes generalize everything we've talked so far about, except locally bounded tree width. So locally bounded tree width is incomparable to bounded expansion, but still captured by nowhere dense classes. So yeah, so this is all I wanted to talk about with respect to structural results, which class is contained in which class, and so forth. So as a summary, nowhere dense are very general and contain all sparse graph classes. And they're exactly those sparse graphs for which you can do first order model checking. And bounded expansion is kind of the little cousin that behaves very similar to nowhere dense, but does not contain locally bounded tree width, for example. Okay, other questions about this so far? If not, then I can already teaser a little bit for the next lecture. So there exists a model checking result for bounded expansion, and there exists a model checking result for nowhere dense graph classes. And let's decompose these results a little bit. So if a class C has bounded expansion, then there exists a function f, such you can decide with a formula holds on a graph from the class in time f of phi times n. So we get an FPT running time, which with a linear dependence in n for the runtime of a model checking algorithm. That is very nice. And next we can see what we can do on nowhere dense graph classes. Here it's a little bit different. So now we no longer get this linear dependence, but for every epsilon, the running time is f of epsilon on phi times n to the 1 plus epsilon. So it's no longer strictly linear, but you can kind of make it as close to linear as you want. So you can get a running time of n to the 1.00001. And the price is that you have to pay is that this function in phi gets bigger and bigger and bigger. So there's a strange relationship between bounded expansion and nowhere denseness that is already visualized by the difference between those two lemmas, and which is that everything that works on bounded expansion also seems to work on nowhere dense graph classes, but in an uglier way. So the ugly difference here is that you get this epsilon into the mix. Of course, if you don't like the epsilon, you can set epsilon to 1, and then you get a quadratic running time. That is fine. But this epsilon will also pop up in different other places. And it's a great source of frustration if you work with nowhere dense graph classes. So that's why when we want to prove these algorithmic results in the future, we will focus only on the case of bounded expansion. So the result that we will prove first will be about existential model checking. And Afterwards, we will also prove full model checking for bounded expansion graph classes. But in the next lecture, we will start with existential model checking. So here we're given an existential formula phi, and we want to again decide in linear FBT time whether it's true. An existential formula, that's something like there exists x1, there exists x2, x3, and then some quantifier formula phi of x1, x2, x3. So existential model checking is basically the same as induced subgraph finding. So this problem is more or less the same as deciding whether some graph H occurs as induced subgraph in a graph G, and deciding this in some function of H times N. Okay, so, but I guess the equivalence and all the algorithms, that's something we deal with next lecture. Otherwise, I'm done with today. So are there any questions about anything we covered so far? Now's the time. If not, then thanks for your attention, and we see each other next Tuesday.